Have you ever really stopped to think about what's going on inside a computer when it, well, thinks? We throw around words like logic and processing, but what does that actually mean down in the silicon? Today, we're going to peel back the layers, starting from the simplest on-off switches and taking it all the way to the brain-inspired circuits of tomorrow. So this whole thing really boils down to two huge questions. First, how do computers actually think? Like, what are the fundamental rules they're playing by? And second, and maybe this is the bigger question, can we get them to think a little more like us? You know, with that kind of gray area, that intuition, instead of just rigid black and white logic. To even begin to answer that, we've got to go all the way back to the beginning. The foundation of all modern computing isn't some super complex grand philosophy. Nope. It's actually built on just a few incredibly simple, almost stubborn rules. We call them logic gates. First up, you've got the AND gate. Think of this one as a super strict bouncer at a club. It looks at input A, then it looks at input B. It needs a yes from input A and a yes from input B to let the signal pass through. If even one of them is a no, the door stays shut. Period. Then you have the OR gate, which is way more chill. This one will give you a true or a 1 on the other side if input A is true or if input B is true. It doesn't even care if both are true. As long as it gets at least one yes, you're good to go. And finally, the simplest one of all, the NOT gate. It's basically the opposite day gate. You give it a 1, it spits back a 0. You give it a 0, you get a 1. Whatever you put in, you get the exact opposite out. And that's basically it. Seriously. Billions, and I mean billions, of these tiny and, or, and NOT gates, all wired together in these mind-bendingly complex patterns. That's what's powering your phone right now. It's all just a giant cascade of simple yes or no questions being asked at unbelievable speeds. But here's the catch. Those super rigid rules, while they're incredibly powerful, can also be kinda inefficient. For the massive, heavy-duty calculations you need for modern AI, being perfectly precise all the time can really slow things down. So engineers came up with a really clever workaround. Okay, so check this out. This table shows the brilliant trade-off they made. On the left is the standard, super precise way computers handle numbers. On the right is a special format just for AI. Now look closely. They chopped the total number of bits in half, from 32 to 16, which saves a ton of space. But look at how they did it. They kept all 8 of the exponent bits. That's what controls how big or small a number can be. But they slashed the anticipates, which controlled the precision, like the digits after the decimal point. It was a very strategic sacrifice. And this quote right here, this is the light bulb moment. The big insight was that for AI, for neural networks, it's way more important to know if a number is huge or tiny than it is to know if it's 3.141592 or 3.141593. For AI, being good enough is actually much, much better than being perfect because it is so much faster. And here's the payoff, and it is huge. By relaxing that need for absolute precision, the actual physical hardware you need to do the math gets 8 times smaller. That is a massive deal. It means you can cram way more processing power into the same tiny chip, which is exactly the magic behind Google's super-fast TPUs. So the big takeaway here is pretty simple. By trading just a little bit of that numerical purity, we get this enormous boost in speed and efficiency. And honestly, that's one of the key reasons today's AI models are as powerful as they are. But even with these clever tricks, we're still fundamentally playing by the same old rules. We're getting really close to the physical limits of how small and how fast we can make circuits based on this simple yes or no system. So to make the next big leap, we're going to need a whole new kind of logic. You know, for decades, every electrical engineering textbook in the world said there were 3 basic fundamental parts to a circuit: the resistor, the capacitor, and the inductor. That was it. But in 1971, a 4th one was theorized, and then in 2008, it was actually built. Everybody, meet the memristor. So what makes the memristor such a game changer? Well, it's basically a resistor that has memory. Its resistance isn't fixed. It actually changes depending on the electricity that's flowed through it in the past. It literally remembers what happened to it, which is just a profoundly different kind of behavior than any other component we've ever had. Okay, so now let's pair this wild new piece of hardware with a different kind of logic, one that's actually been around as an idea since 1943. It's called threshold logic. Instead of a rigid and or rule, a threshold gate looks at all of its inputs, assigns each one a different weight or level of importance, and then adds them all up. It only fires and outputs a 1 if that total sum crosses a certain line, a certain threshold. This slide really makes the difference crystal clear. On the left, you've got our old friend Boolean logic. It's just a series of simple on-off switches. But on the right, threshold logic acts a lot more like a neuron in your brain. It gathers signals, it weighs them based on importance, and then it makes a decision to fire only if the total input is strong enough. It's not a simple yes-no anymore. It's a decision based on the weight of the evidence. So, what happens when you combine this neuron-like logic with a component that can remember things like a brain's synapse? Well, you get the foundation for an entirely new field, neuromorphic computing. Suddenly, the goal isn't just about calculating faster. It's about building computer architectures that are actually inspired by the brain itself. And hey, this is not just a theory on a whiteboard. Look at this circuit. Those little memristors are acting like artificial synapses. You can actually program their resistance to give more weight to certain inputs over others, basically reprogramming the logic of the circuit right there in the hardware. It's a system that can physically learn and adapt. The potential here is just vast. We are talking about everything from way more powerful neural networks and crazy good pattern recognition, all the way to hardware that can completely reconfigure itself to do totally different jobs on the fly. This is a fundamental shift in how we think about building intelligent machines. And don't just take my word for it. As experts in the field are pointing out, this isn't some far-off sci-fi dream. As we really get into the era of nanoscale computing, threshold logic is set to become a major player. It's a huge piece of the puzzle for what comes after our current technology hits its limit. So let's just step back for a second. We've gone on quite a journey here. From this simple on-off switch, through the clever shortcuts that power today's AI, and now we're looking at a brain-inspired future. It's really the story of an evolution, all driven by this constant push to build smarter and more powerful machines. This timeline really puts it all in perspective, doesn't it? These ideas have been brewing for a long, long time. The theory for neuron-like logic, that was back in the 40s. The idea for a memory resistor, the 70s. The first actual device, 2008. And now, all these different threads are coming together to create a brand new path forward. A path that just might take us beyond the limits of Moore's law. You know, that rule that said computers get twice as powerful every 2 years? We're hitting a wall with that, and this could be what's next. Which really just leaves us with one final, kind of mind-bending question. For the better part of a century, we have built these incredible thinking machines on a foundation of absolute, rigid, black and white logic, which is fundamentally different from our own messy, weighted, biological way of making decisions. So what happens when we start to close that gap? What happens when the logic inside the machine starts to look a whole lot more like the logic inside our own heads?